Hello friends, welcome back to the bench. Our patient is two of these. One is the original, one is the one that we need to clone this one into this one. And this is AH63C 2005 Subaru Outback H6 engine, double overhead camshaft. What's wrong with it? The issue actually is pretty interesting. It's the first of its kind that makes it to my bench. The alternator on the car generates 15, I had it, I didn't print the ticket, over 15 volts, right? The alternator should produce 14.4 volts to recharge the battery, right? But it produces over 15 or 16, something like that, which kills the battery over time. Nothing else will happen because we have regulators on everything in the ECM. So even if you supply it with 20, maybe 22 volts, it should still be fine. Most of the caps that you see on the ECMs, the ones that are on the supply rail, they are rated for 30 volts, 24, 30, up to 50 volts. The ones that work on 5-volt rails, so past the regulator, they're rated for 16 volts. So it's kind of typical that the capacitor rating is twice as much as the expected voltage. So nothing will happen there. The car technically works, but the battery eventually dies because of overvoltage. And now I know what you're thinking. How do we know the alternator is not damaged? The regulator on the alternator. We know that's not the case because this ECM comes from Robert from New York, who is an electrical engineer, and he worked in the aerospace industry for nearly 40 years. So he knows how to diagnose, how to eliminate that, right? So obviously he replaced the alternator, he replaced the battery and a few other components, and the same issue. So the issue is somewhere on the ECM. And now, since we have the replacement that we can copy to, this is going to be a fix, right? We're just going to use the replacement. But the question is, which chip is responsible for that? I don't know. So we're going to try to find that chip. But before we do, I want to tell you how the alternator works and what the difference between alternator and the generator is. And the reason I want to tell you that is back in the day I was looking for like a good source of knowledge on the alternator specifically. A main reason for that was I fixed quite a few alternators in my days. And typically, what if the alternator stops working, it stops charging the battery, and you get all kinds of errors on the dash because the voltage is too low. And typically, the issue is that the brushes just worn out, and it no longer generates power because of that, or the brushes are dirty. And that is typical when you have some oil leak. If the oil makes it to the alternator stops producing energy, and then all you have to do, sometimes you don't even have to disassemble it, depending on the build of the alternator. And you can just spray it with gasoline. Blow it with a compressor, and that might help. In other cases, you actually have to disassemble it and clean it inside and reassemble it. But how does the how do you confirm that it's now producing energy? I had a video last year actually. Alternator on my car broke, stopped producing energy, and I tried testing it on the bench, and as expected, I didn't register any when you turn the alternator. I didn't register any voltage spike on the output, and that is always the case. I observed that many times in the past, but I didn't know why that is, right? So I wanted to learn how to actually bench test the alternator, and in that effort, I found some videos on YouTube, and they either are incomplete or slightly wrong. That's why I want to tell you how it actually works. You can go ahead and pause this video. I'll wait, and search for difference between alternator and generator on YouTube, and go ahead and do that, and I'll wait. All right, welcome back. So the main difference that you might have been told is that the generator produces AC while alternator produces DC. While that might be considered correct, that's actually not the difference. I mean, physically it might so happen. Typically generators do produce AC because that's what we want, right? Especially on higher voltages. While an alternator needs to recharge the battery, so naturally the output of the alternator is going to be DC. But they both work on the same principle of magnetic field moving across the coils and inducing current in the coils. So that produces AC. But in alternator you have diodes that rectify the signal, and thus produces the alternator produces this DC. But that's not really a difference. It's the same principle, right? The other difference that you may have been told is that in generator the magnets rotate and the coils are stationary, and in alternator the coils rotate and the magnets are stationary. Again, while that might be true, that's not really the difference, because the principle is the exact same, right? It doesn't really matter which rotates, right? But you may have been told that that's the difference. So you don't need brushes in the generator because the magnets are rotating, right? And if the coils are stationary, you don't need brushes. Again, true, but that's not the difference. That is not entirely correct. Maybe that's not wrong, but that's not entirely correct. So what actually is the difference between the alternator and generator? The difference is the conditions they work in, right? So if you notice the wind turbines, those big ones, if you live in some more rural area, you probably see them driving by, and some of them are turning, some of them are not turning. But when they are turning, they always turn in the same speed, right? Did you notice that? They never run really fast. They always turn at the constant speed, and all of them together. And the explanation you may have come up with for that is that, well, they're right next to one another, so they are experiencing the same wind speed, right? That's why they're turning at the same speed. But they always, regardless what the speed of the wind is, they always turn at the same speed. Did you notice that? The same way, the generators, the hydro power plants, right? You have a dam that it holds a lot of water, and you open a little shaft that lets the water in through the generator, and the generator again rotates at constant speed, right? Because if it starts turning too fast, then you produce more energy. Basically, the phase is different, right? The frequency is different, and you want specific frequency to produce a proper AC signal. Alternator, on the other hand, is mounted on your engine. So the speed of the engine is the speed of the alternator, right? It's not going to be 1-to-1, obviously. Alternator has a much smaller pulley on it than the one coming from the crankshaft. So it's going to turn faster than the actual engine. But the RPMs on the engine at idle, you get, depending on whether it's diesel or gasoline, anywhere from 750 RPM to roughly maybe 900, 950, 920, and that's your idle speed, right? And then as you drive, you typically rev up to, if you don't step on it too much, you rev up to 3,000, maybe 3,500 RPMs. And depending whether you're using whether you have automatic transmission or manual, it's going to fluctuate, right? So we don't have constant speed on the alternator as we do on the generator. That is the key difference. So now, if we have to produce 14.4 volts to recharge the battery, but no more than 14.4, otherwise the battery will suffer, or some other stuff in the car might suffer. How do we control that? Well, obvious solution that you might come up with, perhaps, is maybe let's put the clutch on the alternator, and just depending on how much power we need, we just close the clutch or open, transmitting more or less torque from the engine, right? While that would probably work, you have another clutch that you need to service, and that would be a pain, right? It's not very practical solution, although it would work. So instead, what alternators do, that's why you can't just rotate them and check the terminals, output terminals, to see the voltage. In addition to two terminals, or one terminal for positive and the chassis is the negative, in addition to those two terminals, you typically have 3 more wires going into the alternator. One of those wires, when you want to test whether the ECM is at fault or alternator is at fault, when you either start the car or just turn the ignition without starting the car, one of those pins is going to have roughly 0.2, maybe 0.6 volts at the most, right? And as you start the car, the voltage on that pin will go up. Now, why does that happen? Well, when you start the car, you start it from the battery, right? If you start it from the battery and the alternator, or aka generator, is connected to the engine that you're trying to start, then it's going to work against the starter, right? The Lenz rule. The force that has been created works against the force that created it, right? So if you're inducing a current in the coil by moving the coil across by moving the magnet across the coil, then the coil is gonna work against that magnet, and roughly with the same force that it has generated, right? So the more energy you want to generate in the coil, the more kinetic energy you need to push into it. So that would be not very beneficial if you try to start the car and from the battery, an alternator is trying to recharge that battery at the same time. So you have kind of a closed circuit. So for that reason, ECM needs to be able to control whether we want to pull energy from the battery or from the alternator, but not at the same time. So that voltage on that extra pin dictates how much power we're grabbing from the alternator. How it works exactly, I'm not 100% on it, right? I don't know exactly how it works, but the principle is basically, if instead of having a coils and the magnets, you have coils, magnets, and the coils, right? So you energize the coil to produce magnetic field that interacts with secondary or primary coil, right? Let's call it secondary coil. The more you energize that secondary coil, the more energy you're going to get from the primary coil. And obviously the energy still comes from the coils moving across the magnet or across the magnetic field, right? So the principle is the exact same as the generator. So the problem on this ECM is going to be that it's too bad we didn't test that, and when the customer wrote me about it, I forgot to, well, not really even forgot, I didn't really spend enough time to look into this. It's been pretty busy in the shop, but too bad we didn't check, but we can still check once I send this one back. To check the voltage, when you just turn the ignition, check the voltage on that wire. It should be very low voltage. If, on the other hand, it's more than 6 volts, then the alternator is constantly in the maximum power production state. So this pin on this ECM, the pin was called generator control, and it should have anywhere from 0 to 6.5 volts. So 6.5 is our maximum energy production. So if the RPM on the engine is low, that voltage goes up. As you rev up the engine, that voltage drops because we have more kinetic energy, so we don't want to convert all of that into electrical energy. I assume that the voltage, the output voltage on the alternator has been checked at idle speed, so roughly maybe 900 RPM. Maybe 850, maybe 900. On this engine, yeah, this is H6. It might actually be even closer to 800, maybe 750. Typically, diesels have lower idle speed than gasoline, but it all depends on the configuration of the engine. This is Boxer H6, so it's gonna have relatively low idle speed. And that produces 15 volts in this case at idle speed. But as you rev it up, the voltage should actually go a lot higher. And what is the maximum voltage that the alternator can give you? It's hard to say. I don't think that is specified anywhere in the specification of the alternator. But we can test that. I have one alternator in the garage that I need to rebuild, and once I do, I will perform those tests and learn a little bit more about alternators. But for now, all we need to do is hook into this pin and see if it's shorted to something. If it's shorted to ground, the alternator would not produce any energy, any current. So it's definitely not shorted to ground. If it is shorted, it's shorted to maybe 5 volts or maybe 12 volts. We'll see. It's at B134 pin 22. B134 pin 22. There. So now, first let's check if it's shorted to anything. We also have a second one, so we can compare measurements. 73K to 12 volts. 41K to, I don't know which one is 5 volts, which one's 3.3. So I don't see the short. Oh, it's this resistor. Okay, so we have 1K resistor. Is it? Oh no, this is 100. No, it's actually 10. Yes, because it's 100, right? So that's 10 ohms. We have a cup, and looks like we will probably go all the way to the MCU. It's gonna be an analog output on the MCU. Nope, we have the transistor here. Okay, so if anything is wrong, it's probably this transistor here. Let's take a closer look at it. Alright, it is L81. We have L33. So L81, I don't remember. L33 is NPN, if I remember correctly. 81, it might be PNP. This is the gate, right? And let's see if we can trace. Oh, we cannot. So it goes to VIA. But most likely from here it goes directly to MCU. MCU is going to be what controls the output, right? So in this case, we could replace this transistor, but typically when something goes wrong with these, it is short. But we have no short on it. So this is collector, emitter, and the base. So either the signal on the base is messed up, the output of the MCU could be damaged, and typically, especially on analog outputs, because it's always either open collector or open emitter. In either case, the power goes through internal transistor, and that internal transistor might short out, which in turn would cause this to always be high, right? Or always be low, depending what transistor this is, which in turn produces output signal to always be high. What is it? T831. So either this transistor is faulty, or the output of the MCU is faulty. Now we could trace it further to the MCU, because maybe, well, no, in this case, it's definitely going to be an MCU. And how do I know that? Because all of these chips, this one, and all of these are output stages, right? So some of these control injectors, some control the coils, some control the fan signals, the relays that turn on fans. So the signal from these comes directly from the MCU, right, and goes directly to the output. Now, if there is a transistor on the output, like these, then the base of the transistor will definitely not go to another output stage and then to the MCU. It'll definitely go directly to the MCU, because otherwise you wouldn't need that transistor if you have an output stage, and vice versa. If you don't have a transistor, nothing pretty much goes directly from the harness to the MCU, right? Now, the other possibility here, because there's one more possibility. How does the MCU know how much voltage to send to this pin, right? What the voltage should be. Meaning, how does it know whether to increase the charging or to decrease it? Now, RPM is a good metric. It's probably a part of the equation, most likely. But more reliable is to measure the voltage. We want the voltage to be at 14.4, right? Now, I did not find anything on the sheet that would indicate that it's a sensor, the voltage sensing pin, right? So most likely that voltage is measured somewhere on the board near the input, right? So we expect the input voltage to be at, between 12 volts and 14.4, and the ECM will measure that voltage, and if it's too low, it'll push the alternator a little harder to start producing more. If the voltage is too high, it'll lower it'll start throttling the alternator. So if that sensing circuit is not producing correct result, not producing correct signal, meaning the ECM always thinks that the input voltage is too low. It could be either, perhaps the voltage is completely zero as far as the comparator is concerned. So it always goes to the maximum because the voltage is too low, or the voltage is actually slightly lower than it's supposed to be, and that's what triggers the MCU to start producing more energy and more higher voltage to compensate for that. So both of these are possible. I would say more likely is that the sensing circuit is at fault here. But since this is not something that the user or repair manual will give you, we would have to I'm not even sure where to start, most of the chips on the ECMs are specialty chips, so they start with letter S, which means you're not going to find a data sheet. You might find a replacement chip, usually you can, but you don't know what's in the chip, you don't know how it works, you're not even going to find a pinout for it. There's nothing known because these are specialty chips. They're not on the free market, so there's no need to publish the data sheet. In some cases, if you just replace the first letter from S to M, you can find an equivalent. So it's pretty much the same number, the same chip number, but instead of SC, it's going to be MC. Or instead of SS, it's going to be MS. That sometimes works because the companies that produce these specialty chips, since they already have the die, they already have the process to manufacture them, and perhaps the lease or the agreement times out, right? It expires. And since we already have the ability to produce this chip, then let's change its name slightly and release it as the chip, public chip, with the data sheet and everything, right? That sometimes happens, but you know, it's kind of beyond my capabilities to. You know, I don't do that enough to be this proficient and just be able to find the replacement chip just based on the what it looks like in the circuit, right? Some people can do that. I've had a lot of help from such people in the comments that, you know, they looked at the output, the pinout, and recognized that, yeah, that's going to be a similar chip to that one, right? And it's a completely different markings on the chip. I don't have that ability, so as I said, I don't really even know where to start, so we're not going to attempt that. But if you have an idea, then definitely drop it in the comment. Because that's the main purpose what we're doing here. We just wanted to learn which chip is responsible. And I don't know, technically, we see we have more transistors over here, and they're pretty close to the MCU. And these ones, they are, right, this one, T831, again, is very close to the MCU. That's typical. That's how I know that it's definitely going to be an MCU. Well, that's one of the reasons why I know that it's definitely going to be an MCU on the other side. So yeah, so this is the chip responsible. But again, I suspect that it's going to be the voltage sensing circuit that is going to be at fault, since this transistor doesn't seem to be shorted. And if the transistor is faulty and it's not shorted, then the fault is going to be that it's just not going to open, right? And if it's not going to open, we would expect a low voltage, so no charging, not overcharging. If it's overcharging, then most likely we're just sensing too low of a voltage and compensating. So this part, the output of the MCU and the transistor and the resistor, all of that is most likely fine. We're just telling it to do something that we shouldn't tell it to do because of the measurements. Okay, Robert, I guess this is your answer. I hope you found that useful, and I hope you guys found a explanation of the difference between the generator and alternator more useful than you would find on the other channels with very nice graphics, animations, and all of that stuff. I have none of that, so I have to compensate, giving you more accurate and more detailed information than you can find anywhere else on YouTube. In any case, thank you guys very much for watching. I do appreciate you, and I shall see you in the next one.